So we keep going with periodic operators, the method of gauge transform, number 3.
Thanks. Okay, now back to the magnetic operator. This is what I will study now. Let me even forget about the electric part. It doesn't really matter for our consideration. So I will look only at the magnetic operator with the periodic magnetic potential. Notice that the potential is periodic, not the field which is created by this potential. If the field is periodic, then you have many other effects. For example, if the field is constant, how much more periodic can it get? If the field is constant, then you have, in two-dimensional case, for instance, you have infinitely degenerate eigenvalues, Landau levels. So no questions about absolute continuity. This is why we are going to assume that A is periodic.
The field is periodic here. It is just that it has zero flux.
But
Yes, that's right.
you said not the field, but you meant not just the field.
Not just the field. Yeah, that's right. Yeah. Field, of course, if the potential is periodic, the field is also periodic. But the flux is zero in this case. This is the zero flux case. Right, so theorem. And I will call this theorem AC for obvious reasons. Then H is absolutely continuous for all dimensions starting from 2. Okay. Now let me remind very elementary thing. I will need it a bit later for motivation, but let me just do this. We talk about gauge transform. So let's write the classical gauge transform. So trying to see whether I need those signs. Okay, if phi is a function, let's look at this operator. What does it do? It will be just this. Let's take an infinitely differentiable function for simplicity. Okay, now by choosing this function you can do whatever you can with the magnetic potential. For example, you can assume that the divergence of the magnetic potential is 0. By picking the appropriate function, you can denote this by the new vector potential, and you can assume that the divergence is 0. This is the classical gauge transform. And what we'll also assume, by picking another function, we can assume that the 0th Fourier coefficient of this function is 0 as well. Of course, this is a very elementary thing, but notice what happens in one dimension. In one dimension, you can kill magnetic field altogether. There is no magnetic field in one dimension, we know that. And this elementary fact I will use a bit later. I will find a transform which reduces, in quotes, the operator to something one-dimensional, and then we can kill the field. Fill the field. Okay, so that's the observation. But I will need these two conditions. These are the assumptions. Okay, now let's look at the operator h of k. Right. When we look at the fibers, depending on the quasi-momentum, we get the following. We get h naught of k plus what I denote by g of k. H naught of k is the ampere-turk part. Or let me denote this by d. This is the standard notation. D plus k squared. And the second, the perturbed part will be minus 2a d plus k plus a squared. Okay? There is no derivative term for a because of that condition that I imposed. Divergence is 0. It's convenient. Now, as we now understand, it is good to take k into complex plane. This is what I will do. I will define a family of operators depending on the parameter that I will denote rho, and it is defined like that. I will take h of k, and then I will add a complex component to that k. Rho is a number, and alpha is a unit vector. So I choose a direction in the d-dimensional space and extend in this direction this component of the vector k. Okay? So I'm extending it I'm looking at the function of one complex variable here, okay, in the direction alpha. Before what I should have said a few minutes ago is that you remember we defined these operators on the dual domain, right? So on the cube, essentially. But because of this wonderful property that all these operators, they are defined on the same domain, we can now consider this as an analytic family of operators. So k can be real valued or complex valued in general, anything you want. The important thing is that the domain is the same, and then you can use all the benefits of the perturbation, classical perturbation, analytic perturbation theory. Okay? But I will use those benefits only for perturbation in one complex variable, as a function of one complex variable. Not many variables, as in this formula, k is a vector, but I will use only one complex variable in direction alpha. Direction alpha here is not only for generality, but because it is important to choose the right direction. I will come to that a bit later. You will see why it is important. What I want to do now, I want just to write further formulae. Let's see how we can rewrite this for this new operator. The rest, you see, this operator depends on rho, and I don't care about the dependence on k, so this is the parameter which can be temporarily omitted. Now let's write this down. So we'll just write h of rho is h of h naught plus I have the perturbed part. This is handwritten g, so h naught. This time I want to write it as a pseudo differential operator. This will be convenient for me. H naught it will be psi squared plus or minus plus alpha times psi. Rho is here, we can't do anything about it, minus rho squared. So that's the symbol. I remind you that psi is nothing but theta plus k. Theta is the vector of the dual lattice. We can assume that dual lattice is integer just for simplicity, and k is the quasi-momentum. Now the perturbed bit is minus 2a psi. Let me just see. Yeah. Minus 2I rho A times alpha plus mu x squared. I think this is correct. So that is the perturbation. Right. Now, what is the relationship between these two parts? Well, it is a very straightforward exercise to write the following. Now, if you, let me just try this, what is easy to get, we can explicitly write down the estimate for this perturbed operator via the unperturbed one. By the way, here, this is not the operator, that's the symbol. Let me write the symbol here. Okay, so G of rho is operator with symbol G. Of course, the symbol depends on rho, but I will drop this just for brevity. Now, what is easy to do is the following. So G rho this is on the torus. What is what here? So rho is, we already know what it is, H naught. Everything is clear except for A. A is the maximum of the magnetic potential here. So this formula shows, so this estimate shows that, and of course there must be some constant here as well, that this operator, as we expected, is infinitesimally bounded by H naught.
So that is the calligraphic G, right?
Oh, sorry, calligraph. Yes, this. Yeah. And what is also useful is that this A is here. So if we take a very small a, the overall thing is going to be small. Okay. Now, let me do this. Now, I will split this K into two components. One of them aligned with alpha, and the other is orthogonal to alpha. So K, the part of K aligned with alpha, and the other orthogonal. So orthogonal will be orthogonal to alpha, and the one which is aligned will be just beta alpha. So beta is a number, alpha is the vector. Okay, so beta is the coordinate of this K parallel. Now I'm ready to state the theorem. This is the theorem that converts the qualitative information in theorem AC, absolute continuity, into quantitative information. So I'm going to write an estimate, which would imply that theorem straight away. This is theorem which I label T, after Thomas, is this. So, there exists a number rho naught, which depends on the magnetic potential, and a vector of the dual lattice such that for the unit vector alpha defined as the direction vector of this vector of the unit lattice, one has Okay, for all smooth functions on the torus and sufficiently large rho. Rho is greater than or equal to rho naught.
Does it suddenly become important that it's the unit lattice instead of the
No.
Gaussian?
It doesn't matter at all. I dropped the assumption of generality just not to write extra things, that's all. Otherwise I would... It doesn't matter. It's not important. Now, what does this theorem imply? We talked about this a few times. I talked about this a few times before, last hour and on Friday, and Peter talked about this as well. This kind of estimate would imply that there are no constant eigenvalues for the operator h of k, and therefore there is absolute continuity. Okay. I wouldn't like to say anything else about this, although we could discuss that, but it would take another 15 minutes or so. So let's just accept this with reference to Peter's lectures, that this estimate implies that h of rho obviously grows when rho tends to infinity, and therefore there are no constant eigenvalues for this operator, and as a result the spectrum is absolutely continuous. Theorem T implies theorem AC. So that's the fact that I want to accept now. Okay, once we accepted this fact, how do we prove theorem T? Let's look at those operators again. So we have H naught over there, and we have the perturbation. Let's look at H naught. It is very easy to get this bound for H naught. Look at the symbol. So there's the real part of the symbol here, xi squared minus rho squared, which is not so good, because xi squared can actually hit rho squared, right? And that will be 0, so it will not give us any bound. No hope here. However, we have the imaginary part. Okay, let's look at the imaginary part. So how to prove theorem T for H naught rho. I'm looking at the imaginary part here, so this will be 2I rho alpha times xi. You remember xi is lattice point plus k. And because we're multiplying by alpha, I can leave only the parallel bit. You remember what alpha is? Alpha is this vector, integer divided by its length. So we can rewrite this. Okay, so n times this. In here I have beta times alpha. So I have beta times alpha, which is that. Okay, doesn't move. Let's simplify this. There's what?
So it's alpha dot psi.
There's extra n, that's right. That's correct. Okay, let me just simplify that. So what is going to happen now? We have here n times theta. This is something which is always integer, So let's take beta in such a way that it doesn't fall into integers, this product. So let's take beta to be 1 over 2n. Okay? And then this guy is going to be bounded. It will be from below by that times 1 over 2n times n times 1/2. Right? So it will be rho divided by n. Okay? This is a very simple calculation. So if we fix beta, as I indicated over there, we get this lower bound. So for the unperturbed operator, this is okay. We can get that very quickly. And this tells me that I should also specify beta in this theorem. Right? Because beta, the choice of beta is very, very specific. Right. Now, suppose that we turn the magnetic field on. Now, this operator, this symbol is non-trivial. We have this bound here. It's a very convenient bound. If your parameter A is small, then the magnetic field is not going to spoil things too much. Right? If we take that it's so small that this coefficient, it is less than 1 over n, over norm of n, we will still have the same bound with a different constant. But the bound will be the same for small a. This is exactly what two of our colleagues did. Rainer Hempel and Ira Herbst. They did this, and in the beginning of the 90s, they made this observation that Thomas method actually works for small magnetic fields. If the magnetic field is not small, we can't do much. There is nothing we can do here using this kind of argument. So we have to get rid of the magnetic field. That's a good plan, to get rid of the magnetic field. Another thing I wanted you to to notice in this theorem is that I claim that there exists a vector such that we have this bound. It is important to choose the right direction in which we extend the parameters into the complex plane. If we do it just along first or second direction, anything, just arbitrary direction, is not going to work. We are not going to get this bound. This argument will work only if we choose it in a very, very specific way. I will describe how to do that. I hope to describe it in the next half an hour. The first thing I want to suggest is this. We still have this bound, right? But A is not small. So what I think we should do, we should split this space into two, the space, I mean L2 on the torus. This is where we study those operators, into two subspaces. And here is the description of those two subspaces. Orthogonal. These subspaces will be spanned by exponentials with certain exponents, with certain indices, and I want to split L2 on the sphere, on the torus, excuse me, into two subspaces. They will be described by these sets. This is the first set. These are the points of the lattice such that m minus rho is less than omega. Okay. Sorry, excuse me, m plus k minus rho, to be precise. So what we have here, we have a sphere of radius rho, and then I identify the points, lattice points in the dual lattice, such that these points are in the vicinity of the sphere, in the omega neighborhood of the sphere. Okay? This sphere is centered at the point minus k, as you can see. Right? So I cut out a spherical layer around the sphere of size omega. And the second set will be just whatever remains. Okay, so we have ZD minus M. Everything else. Why is it convenient? Because on this complementary set N, we can work now with the real part of the symbol. Now I'm going to talk about this little technique here. We can look at the real part of the symbol. Let's see. Xi minus rho squared. Remember that lattice points, that Xi is just m plus k. Okay. Now, if we split this in the trivial way, right? To split this in the trivial way, this is going to be separated from 0 by omega, and this is greater than rho. So this is, I should take the absolute value, of course, it's greater than omega rho. Okay, very nice.
On n?
Sorry?
On n.
No? On n.
Complement.
That's right. Sorry. On n.
Uh-huh.
Outside the sphere, outside the spherical layer, we have this nice bound. Why is it good? Because if we take omega larger than this, then we can estimate the whole operator on that subspace associated with lattice points outside the spherical layer and get a good estimate. I'm going to write this now. H of rho. Now I have to denote, I have to introduce the notation for this projection on the subspace, and that it will be Pn. This is a natural notation, right? This is projection on the subspace of exponentials associated with that subspace. And this will be bounded by 0. Or I can even write omega minus A rho u, right? For large omega. Correction, it should be on the subspace. And well, I need to define it where Pn is the projection, or in other words, Pn is just the operator to the differential operator with this symbol. This is just the characteristic function of the set N. Okay? And this is exactly the projection on the subspace spanned by those exponentials. So this is a very straightforward argument, of course, and this is not difficult to derive this estimate. But now what to do with the remaining subspace, with the spherical shell, with the subspace spanned by exponentials associated with the spherical shell? Well, the advantage of this subspace is that you have finitely many of exponentials, and this is a bounded set. Okay, so that's the only advantage of it. And here I want to show you that on this subspace we can actually reduce the operator to something one-dimensional. The magnetic operator to something one-dimensional. And I will define this one-dimensional object straight away. Hang on. Right. This is going to be an operator which I denote by TA, depending on the magnetic potential. D plus K. And then we have here I alpha plus, and here there is something that I'm going to define in a few seconds, minus rho. This is the unit vector looking in direction D plus K.
And you have inner product
between these two? Dot. Yeah. Let me write it in the symbolic form. It will look a bit better, although not too much. Well, hang on a second. I missed the magnetic component here, the magnetic field. That's the object. The symbol of TLA is this. It is Xi minus A. Okay. So why do I call it one-dimensional? Because there is scalar product here. This gives you a scalar, so it is kind of derivative in one direction specified by this vector. This is why I call it one-dimensional. And this is what will make it work. So why is this operator good? Because of the following fact. And this is a lemma which is crucial for the method, is that when you take h of rho and replace it by this operator times 2 to rho, and you do it on the subspace M, then the mistake that you make is of order omega squared or something like that. In any case, this is a constant which doesn't depend on rho. This is omega squared. Okay, with the prefactor depending on the magnetic field, of course, but we don't care about this at the moment. Okay, so now the second order operator is reduced to the first order operator, which we will study in a few minutes. Why is it true? This is a very simple calculation. Let's look at the symbols again. So let's look at this symbol here, for example. So we have here, this is a very quick idea of the proof. So Xi squared plus 2I alpha Xi minus rho squared. This is the symbol of H naught. And it will be, I take these two guys together. This one is already in the required form. There is rho here. These two guys, they look like that, minus rho plus rho. Now, what's the difference? What do I want to do? I want to replace this psi by rho because it is very close. It is in the spherical shell, right? So I will replace it by rho. And it will give me 2 rho here. The error that we make is exactly of order omega squared because psi is in the spherical shell. Plus 2I rho alpha psi. What is this here? This is nothing but psi times the direction vector. This is scalar product here. And now I can rewrite this by taking this direction vector out. And this will give me, okay, I have to finish writing on this board. So it's going to be psi two rho psi times that. That's that guy. Then the next term is this. And then the remaining term is 2 rho squared. Okay? So the mistake that I made on the way to this answer was of size omega squared, right? So the norm of the perturbation cannot exceed omega squared as claimed. Now, what to do with the second bit of the symbol, the perturbed one? We're doing this in exactly the same way. So this term, let me write this down. Not here. Here. Now, I will not rewrite this symbol. Let me just drop this part because it will be of a constant size contribution. I don't worry about this. And this, well, actually, we don't have to do anything at all except for one little thing. We need to get rid of this psi here. So let me do 2a. So it is almost the same as this operator, or this symbol. As I said, I dropped a squared. I don't look at it. It is constant contribution. Here, I replace this psi by direction vector times rho, right? In the spherical shell, I can do that. The error will be of order omega. And this term stays as it was before. And that's it. This is exactly what we are looking for. Minus 2 rho a times I alpha okay. So now if we take the unperturbed part here, combine it with the perturbed part, we will get exactly this symbol. All right? We will get exactly this symbol and 2 rho as a prefactor. So we got this reduction to the first order operator. Now, can we diagonalize the first order operator? That's the question. Now we can get rid of we want to get rid of the magnetic potential now in this formula. Now, why do we want to do that? Because if we didn't have A, then it would be very easy to get the bound of the following type. This is what we want, isn't it? Although on the subspace PM, on the subspace M, for all the vectors, for all the functions in the spherical shell here, whose Fourier coefficients are associated with exponentials in the spherical shell. This is what we want. If the magnetic potential is absent, then as before, as we did for H naught, you remember that was a very simple calculation. Let's look at this operator here. So A is not there. Let's look at the imaginary bit, the bit that contains I here. So D plus K is just Xi. This is what we want, right? We multiply Xi by this combination, but we consider only the imaginary bit, more precisely the part containing I of this factor. So this is what we want. And again, this is the same calculation as before, if you remember. This is theta plus k orthogonal alpha, and repeating the same argument, what we would get is 1 over 2n again, if we choose beta as before. Right, so beta is the coefficient in front of alpha here. Okay, so if alpha if the magnetic potential is absent, we can immediately estimate this by something from below. Okay, the crucial point here that we have the imaginary unity here. Right, so we can take the imaginary part and estimate it. We don't care about the real part. All right. Now comes, at the end of our 3, comes the gauge transform. So now we need to get rid of it using the gauge transform. You remember I explained that in the classical elementary gauge transform, in the one-dimensional case, you can always find the function in such a way that the magnetic field will be killed. Sorry, magnetic potential will be killed. So this is what we're going to do here, because we have a one-dimensional situation. Let me write the formula now. So let phi. So now I will take a symbol phi from what class? From class S0 on the torus. Let me skip specifying the weight for this class S0. I will do it a bit later. We will find this out automatically when we solve the equations that pop out. I will define the following transformation. Right? So this is the exponential of a pseudo-differential operator on the torus. And now, let's look at the similarity transformation. We will take the operator TA and consider the following similarity. Here we have W and W minus 1. And there is a classical straightforward formula for that.
So your W is not unitary, right?
No, it is not. And it cannot be unitary because this is non-self-adjoint problem. Sorry? Exponential function. for a bounded operator, this is going to be bounded. For bounded operators, it is straightforward. I could have introduced Fourier integral operators as well, but I don't. I don't want to do that. I agree. So let's write the standard formula. How do you rewrite this? This is some kind of Duhamel formula, or maybe there are some other names for it. So let's write this down. So first of all, we have TA. This is the first term. Then we have TA commuting with this operator, which I denote now by capital Phi. So this is capital Phi here. Okay. And the last bit is the integral, double integral. Phi with minus. And inside we have the double commutator. Hang on. There is another variable, and we integrate in this variable up to t, and then we integrate in t again. This is you can continue this formula, you can continue extracting commutators from this formula. So the next iteration will be first commutator plus second commutator, and then the third one will be inside, and so on and so forth. You can extract as many commutators as we want, and that number plus 1 will be inside the integral. This is the same formula we are going to use obviously next time on Thursday, when I will be doing something else. I will be working with a different problem, but with the same method. Okay? So here we are. Let's now look what happens when we commute this operator with something, and what kind of information, what kind of benefits we can extract from it. I will not be very careful about the second commutators, because with the things that we obtain at the end of this process, the second commutator will be small, and therefore this term can be considered as a perturbation of a smaller order. In other words, the second commutator will give a contribution that tends to 0. Right. Yeah. All right, let's write out. Now, minus 1 TA W. TA, it is T naught. Right, so TA, I'm looking at that definition. It is T naught minus A times A alpha plus mu. Okay, this is TA. Now the commutator. In the commutator, I will keep one term. So to take the commutator, I have to commute 2 bits with phi. The first factor and the second one. I will commute the first one and I will get d phi, this commutator, times phi alpha plus mu. And let me just drop the rest. Let's forget about the rest. It will be also kind of small. Now, what I would like to do, so T naught I know how to handle. It has a nice lower bound. I want to find the symbol phi in such a way that these two guys kill each other. They compensate. Yep.
What happens? Why does the mu no longer multiply t plus k?
It is not multiplied by what?
So on the upper blackboard you have mu times t plus k.
Yeah.
The lower you don't have it.
Nu is a function.
Sorry.
I'm sorry. Nu is a function.
Okay.
I'm very.
There's a D plus K there. They just didn't write it.
There is d plus k. I didn't write it. Yes. So I don't like writing d plus k. I like writing psi, but it's not always appropriate. So this is why I didn't write it. And I was very happy that I could answer a question. So here we are. Now let's choose phi in such a way that it kills. So this is the equation. This is the commutator equation that we want to solve. This is d phi. This is capital phi equals A equals that. Scalar product. This is a scalar equation. Now, it has been erased a long time ago, an hour or maybe more, how to find the symbol of the commutator. Let's just write it out. More precisely, I will write the Fourier coefficients of the symbol, okay? If I write Fourier coefficients, I will get this. It will be phi, and then I have theta psi, right? So this is the symbol depends on two variables x, psi. Fourier coefficient depends on dual lattice points psi. And then here I will have theta I alpha theta plus mu psi theta equals, this is the left hand side, and the right hand side will be a psi, ax, excuse me, and here I have I alpha. Okay? This is a very good equation. We can solve it by dividing by this factor. Linear equation. Well, the only issue is this factor non-zero? That's what we have to ensure. Where do I write that? Solution. So let me write the solution first, and then I will comment on the denominator, just to make sure that this is not zero. So this solution provides us with Fourier coefficients of the symbol that solve the commutator equation. Now ax theta times I alpha divided by okay, that's the solution. Now what I want to do, I don't have much control over this, because this thing, the direction times the vector, that can turn into zero depending on psi. Here theta, notice that, oh excuse me, I made something, nobody corrected me, but I correct myself. This is the Fourier coefficient, I'm sorry. So that's the Fourier coefficient. So let's assume, for simplicity, it doesn't have to be, eventually this condition can be lifted at the end, but for the time being assume that A is a trigonometric polynomial. It has finitely many Fourier coefficients. So outside of ball of radius L, this is zero. Okay. So here we have finitely many values of theta that are dangerous, where this product can turn into 0. Now I'm going to choose this vector alpha. You remember I said in the beginning I have to choose it in a specific way. I will choose it in a way which is non-orthogonal to any of those vectors inside the ball. And, well, this is kind of obvious that this can be done, but I have a nice procedure just which gives you exactly the coordinates of this vector n. So let me just tell you what it is. So let R and L be just positive integers, and we define n as a vector with components and j. So j will run from 1 to d in the following way. This is R, L, j minus 1. Okay? So when you increase j, the powers are increased, so the vector becomes very long. The further you go, the further you approach d, the longer the components become. And then, let me just check that. Yeah, that's correct. And then if, is it greater? Hang on, yes. So if R is greater than d, if you take R greater than d, then alpha, then n and theta is not 0 for all theta inside the ball. Okay? That's exactly what I want. So if I choose n like that for given L, then I will never have orthogonality. This is how this direction alpha is chosen. Choose just the direction of vector n like this. And then, you have a nice formula for the Fourier coefficients. This is something which is not 0. And actually it is separated from 0 by a universal constant. And there is I here. So the denominator is never 0. Fantastic. This is something that will diagonalize the operator TA. And before we go on the, 2 minutes, thanks. Before we go on the break, the presence of I, it is just our luck in this problem, because it came from the fact that we went away from the real line into the complex plane. This I comes from this continuation into the complex plane. If we stayed on the real line, I don't know what kind of things we would do there to prove the result, but if we stayed on the real line, we would have had a serious problem in the denominator. It could turn into 0, and this would really create physically relevant problems. We would have so-called resonance zones, right? For certain thetas, for certain directions here, we would have resonance zones, and we would have to study those zones separately. This is what we will encounter in the next problem when I will talk about Bethe-Sommerfeld conjecture. This is where we have to handle those zones specifically. But this is a very easy problem, because we don't have resonance zones. And once we have that, we will diagonalize the operator TA, and I will continue in, can we have 5 minutes? Because I understand it's better to finish well in advance of, relatively well in advance of 5 o'clock, because of the next lecture. There will be quite a few people, it seems. So let's have 5 minutes perhaps.
Yes. Is there any question? Okay, so let's have 5-minute break and then we continue.
Thank you.